Welcome back, everyone. Today we're going to be covering 5.D, the least square regression line. So up to now what we've done is we came up with the least square regression coefficient to see how strong the line was, and we came up with the best fit I line to kind of just like use the mean point and draw where the line is. But now what we're going to do is we're going to actually come up with the equation for the line. And this is all done in a very similar manner using the same technology we used before. So after today's lesson, or this week's lesson, you're going to be able to understand how to find and interpret a least square regression line, draw a scatter diagram, continue, we learned this before, but we'll keep on doing it, calculate and use the regression coefficient, R, comprehend the relationship between the variables, okay, we're going to have two variables, one on the dependent and independent axes, and then create a regression plot, right? So let us get started again. The problem with drawing a line of best fit I, our last lesson, is very simple. It could vary from one person to another. Now we all have the same mean point, okay? Everyone's X with the line over it, Y with the line over it, are all the same. That point's the same. But you may tilt your line, instead of being like this, you may tilt it up a little bit or tilt it down a little bit. So it's not exactly precise. Now we're going to get to precise, okay? So for consistency, we're going to use a method known as linear regression. Right? The most common, is least square. And this is how it works mathematically. Now, linear regression itself, it's going to find the equation, the actual equation. So it's a y equals mx plus b. You're going to find your m, which is your gradient, and you're going to find your b, which is your intercept, y-intercept, or whatever type of intercept it is. So, and we're going to do that using the least squares method. All right? Now, here's an example. You have point 1, 2, 3, 4, and 5 for a line y equals ax plus b. Now, what least squares regression does is very simple. It's the sum of the squares of the vertical distances between the point and the regression line is minimized. What does that mean? That means what they do is they actually figure out where to draw this line so that when you add up all the sums of the vertical lines, it's the smallest number. Because if I tilted it, say, take this point, and I tilted it down this way, this vertical one would be longer, and this one would be smaller. So you want to know the exact tilt, where then you add them together and add everyone together, you get the lowest number. And what they do is they do this by finding the distances between each point and the regression line. Each point and the regression line. And when you add all those points up together, all these distances together, you want the smallest amount, and then the line fits in between. And this is done with a crazy mathematical formula that we'll get into, but you don't really need to know how to produce or use, just how to use the calculator. All right, and let's go. In this course, you will not be required to find the equation for least square regression by hand. Instead, you can use your graphing calculator or the statistical package that is in the online book, okay? For the terms of me teaching you guys, I'm going to teach you how to do everything with the graphing calculator, because when you're done with IB class, you're not going to have the IB statistical package anymore. But we will go over that in class as a little extra. Now, here's how to use this calculator. To find the regression line for data, we're going to enter the x values in for L1 and the y values in for L2. Now, in order to do that, in case you guys forgot, you take your calculator. Okay, you want your list cleared, so you can press second. Oops. The calculator just froze on me. That's not good. All right, so I turn my calculator on. I want to clear my list. So in case you guys forgot to clear your list, you hit, let me go back to this method. This way actually didn't work too bad in the other class. Second, and then you hit mem, okay, which is the plus. Oops, I hit y equal. All right, and then when you get to here, you're just going to hit number 3, which is clear all entries, enter, and done, and now you got it. Now we're going to enter in our x values for L1 and our y values for L2. So you just hit stat right here, and then you hit enter for edit, and you're going to type all those values into your calculator. Okay, so I want you guys to do this with me. So type in for your x's, I'm doing this as I say this, 55, 36, 25, 47, 60, 64, 42, and 50. Now I messed up one of my numbers, so I'm going back. And I'm just fixing it, 64. And my L1s look like this. After I type in my L1s, I press to the right button right here again, and it goes to the L2 column. And then I'm going to enter in my L2s. All right, 120, 90, 60, 160, 190, 250, 110, and 150. See, I'm doing this right with you, real time. So now this is what we have in our graph. Now what you're going to do next is you're going to hit the Stat button. You're going to press Stat and select number 4, which is Lin Reg, AX plus B from the Calc menu. Okay, so it looks like this. So, got my calculator. I got my list nice and good. I'm going to hit the Stat button, which is right here. Now, Edit's where my list is. I press to the right one, and I go to Calc. Okay, I'm going to go down to number 4, where it says Lin Reg. That's linear regression of AX plus B. I press a bunch of enters to go to Calculate. And there we go, AX plus B. Now, notice it doesn't give us our regression line, okay? We didn't really need that one. We didn't really care for that right now. I mean, it just gives us our regression line. So since it gives us this stuff, what we're going to do is we get this. And this is what mine says. Wait a second. Mine was different. Uh-oh. What did I mess up on? Oh, I put 12 instead of 120. I lied to you. See, I had 12 instead of 120. So now I'm going to go back here. I go, oh no, my answer's wrong. Get back there. And then I hit Stat, Calc, and I change it real quick. And I calculate, and there we go. 4.17, negative 56.69, so 4.18, negative 56.7. All right, and I'm going to use them to get my regression line. And the way I do that is, A is my slope, is my gradient, 4.17 is my gradient, negative 56 is my y. So my regression line is, I'm going to round up, y equals 4.18x minus 56.7. Notice I'm going to 3 significant figures. Okay, if you want to know if this is a good regression line, you could say, okay, is this a good one? Well, what you could do is, in your calculator, remember to get the regression coefficient, you have to take mode, and when you go down to, nope, not mode, where are we at? Oh, I lost it. I'll get back to it. You have to go back into, you have to turn on your regression line. You do that with catalog. I can't find catalog right now. It's in there somewhere. You can use catalog. This is another way to do it. Catalog is the second button and the 0 button. All right. Oh, I don't show it here. And what you go down to is you can actually press alpha and all these letters. All right, and that'll bring you down there. So if I went alpha T, it'd bring me to like tangent, oops, sorry, stuff like that. I don't want that, I want regression, so I go alpha R. Then I can go down here. Nope, alpha regression's not there. It's somewhere, Lin Reg, no, coefficient. Well, anyway, it's in there somewhere, and then you turn it on. I lost it for some reason. Can't believe I lost it. Oh well. It went off on a tangent. Well, we know how to find the regression line. All right, so what we're going to do is, example 4, I want you guys to first construct the scatter diagram. Oh, I'll just go look at my notes. As I look at my notes, let's remember how to put the regression line in it. All right, so you're writing down your scatter plot. Scatter plot, scatter plot, scatter plot. mode. Oh, it was there. I just didn't go to the right one. All right, to get the regression, you go to mode, down to stat diagnostics, and turn that on. I just didn't see it. So now I'm gonna have my regression coefficient pop up anytime. Anyway, you guys should draw your scatter diagram. Looks something like this, okay? You have your points right here. So as you can see, the graph does look like it has some type of a linear thing going up. Now what you're gonna do is you're gonna use technology to find the regression coefficient. So once again, with technology, you're gonna type in those numbers. Okay, so if I type in my calculator, all right, I go to second mem, I'm gonna press 3, clear my entries, go back to list, edit, whoops, clear list, what did I do? Oh yeah, 4, right, clear all lists. Clear all lists, which is number 4. I go to stat, edit, I have empty lists here, and I'm gonna type in those two lists, okay? 55, 36, 25. So you can't say I'm going too fast. 47, 60, 64, 42, 50, whoops, 50, and then this was supposed to be a 64. All right, so that's my first column. Second column. I'll do some of my own.
Interruption, teachers, in case you have not checked your email, tomorrow
120.
will be a virtual day for everyone.
Snow day tomorrow.
Due to the anticipated inclement weather.
That's why I'm making sure I get a bunch of lessons done today. All right, so we get all our lists typed in, right? So list 1, list 2 are in. Now we're going to find the regression line. You hit, once again, stat. Okay, press to the right one's calc. Go down to linreg. Enter, a bunch of enters, and there's my list. And now I got my regression coefficient. Notice the regression coefficient is about 0.89, which is about 0.9, which is a strong, not perfect, but it is a strong linear coefficient, which is good. Now notice A is 4.178, B is negative 56.69. So you're going to take those numbers, and you're going to round those numbers. And when you round those numbers, this is what I get right here. My linear coefficient is approximately 4.18x minus 56.7. And there we go. If this continued down here, intercept here at like a negative 56.7, and you're going up 4.8 over 1 the whole graph. Right? That seems pretty easy, doesn't it? Just using technology. State and interpret the gradient. The gradient is another word for slope. So the gradient is 4.18. Now, what exactly does that mean? Well, let's see. This is the average income and average grocery bill for a selection of families. Okay, so that means for every, what? We have grocery bill related to income. So for every $1,000 of income, every 1 unit you move over, the weekly grocery bill increases by 4.18 pounds. Right. That's it. Now we're going to start using these lines to interpret the data. So we're going to go up a little. We're going to take example 4. Now we're going to do D and E. Now D says estimate the weekly grocery bill for a family that has an annual income of 95,000 pounds. So what you're going to do is, you know, X is 95,000. So what do you think you have to use right there? You have to use the equation we just found. So we're going to take our equation that we just found. Y is approximately 4.18x minus 56.7. And what do you do with that 95? You're going to take that 95 and do what with it? You're going to plug it into that equation. Okay? So that's what I want you guys to do. And I want you to tell me what you think the annual grocery bill is going to be. And you notice if you did print out the packets, there are some empty spaces. That's for you guys just to do some extra work on what you do. All right? 4.18 times 95 minus 56.7 is approximately 340. Okay, now 340, I go look at my units. My units is pounds. So the little L looking thing with the 340 is my answer. 340 pounds. Now what you're going to do is E and F. You're going to estimate the annual income of a family whose now their grocery bill is 100 pounds. So we're not plugging in the 100 pounds for X. The 100 pounds is my dependent variable. Let's see if you can figure that one out. All right, I gave you plenty of time there. We're going to use the same equation, but since in this case the Y is the 100, so 100 equals 4.18x minus 56.7. Now you just do simple algebra. You're going to add 56.7 to both sides. 156.7 equals 4.18x. You're going to divide both sides by 4.18, and you get x is approximately 37.5. Now it's not 37.5 pounds, that's the income, and the income is in thousands of pounds. So your answer is 37.5 thousand or 37,500 pounds. Right? See? Pretty nice. Comment on whether the estimates in D or E are likely to be reliable. Okay, so how do we know if these are reliable? We have to think back to last lesson with the interpolation and the extrapolation, okay? Now, we're dealing with a dependent variable, which is our income. So pretty much our lowest income is 25, all right? And our highest income here is 64. So everything between 25 and 64 should be good, as long as we have an X in there. Now, what's this X right here? 95, that's way outside our thing. So does that seem very likely? Well, it could be true, but it's really outside the range of the data that we're using to solve this problem. So let's look at the next one, E. If the grocery bill is about 100, well, does 100 fall really in our range right here? Well, we have like 120, okay, we have 60 as our lowest, 250 is our highest. So 100 falls in our data set of our Y. So it probably does seem like this is a realistic answer. And then we go look at back and we go, okay, 37.5. 37.5 is between 25 and 64. So that's the one we're going to use. So D is an extrapolation. Okay, that's outside our answers. So may not be reliable. On the other hand, E is an interpolation. It's between our graph. So that is a strong linear correlation between the variables. I told you before, the R was about 0.9, so that's good. So the estimate is expected to be reliable. So this is really good data. This is possibly good, but we're not sure. Okay, now, just to show you what I'm talking about here, remember, let's just think of two things right here. X equals 95, I'm going to go backwards a little bit extra. You might already get this. And this one was that, I can't draw these L's. The L, however we draw these L's, 37.5. If we go back real quick, this is the problem, but only one board. I can't do the graph on here. Okay, this one, 95. Well, our data here is between 25 and, say, 65. So our data 95 would be over here, so we don't know if that's continuing to be true. 37.5. Right back here. So that data falls inside our area, inside our range. So it's probably more likely to be true. Okay, you only want data in this range to see if it's good. All right. Hopefully you're getting that. I'll annotate all over my WebEx if you need extra help. All right, so back to the graphic calculator. We're going to use graphic calculators for this. I want you to take number 1, and I want you to draw the data set for that calculator. Oh, sorry. I want you to draw the scatter diagram. Okay? So go, draw your scatter diagram. And then what we're going to do is we're going to type in the data set. And like I said, I'm going to type it in with you. This time to make sure class stays on point. I'm going to do this on the video to keep it real time. So, time, unpause. You guys' data set should be good. Pretty good, right? All right, so it shoots up there. It's rising. Looks pretty interesting, right? I think it's pretty linear. Now we're going to use technology, though, to find a regression line. So all your points should be good. All right, now, you doing your data yet? I'll give you a lead. All right, second mem. I'm going to clear all my lists, number 4, and I'm going to hit stat. I'm going to hit edit. I'm not going to zoom in on this one. I'm just going to let you guys go. 10, 4, 6, 8, 9. This is quick. 5, 7, 1, 2, 3. Ah, I did it in the wrong column. 6, 8, 9, 5, 7, 1, 2, 3. All right, then the other ones. You probably beat me because I messed this up. All right, 26, 8, 13, 20, 12, 13, 4, 2, 7. All right, got it. So you got all your lists in there, right? So we got, okay, good. We got our list ready to go. Come back here. Okay, I'm gonna hit the word stat. I'm gonna hit calc. I'm gonna go down to number 4, Lin Reg. And boom, there we go. I got a regression line of 0.93, the R. Regression coefficient, 0.94 about, 0.93. That's a very strong one. Okay, A is 1.92, B is negative 0.666667. You're gonna round to 2 decimal places. So when you round to the 2 decimal places, you end up with 1.92x minus 0.0667. I don't know why I said 2 decimal places. What I really meant was you're going to go to 3 significant figures. Sorry, I'm just checking big through. Now we're going to use B to draw a regression line. Okay, way we draw a regression line is our y-intercept is at 0.0667. So I put a point right down here. I put it in green at 0.667. And then 1.92 means I'm going to go up about 2, and I'm going to go over 1. So I'm right about here. And then I'm going to connect these points. Oh, there you go, B. My y-intercept is negative 0.0667. My slope is 1.92. Connect the points, and look what happens with my line. Boom, goes perfectly through here. If you found the mean of the top and the mean of the bottom, put that point would fall on that line. But you wouldn't know if our tilt would line to get there. How do you like these? This part of the lesson's easy. Problem number, whatever this is. More calculator work. All right, so now we're going to do a regression line on the scatter diagram. Okay, so this is a little bit extra, not too much. So, first thing you're going to do is you're going to enter all these values into your calculator, and I want to know what's up. All right, now, if you want, I'll enter them with you. All right, and we'll practice just typing this in. This is kind of repeating what we just did, but what it does is it just gives you a little bit more practice, which is good. So I'm going to go first to second mem. I'm going to hit 4, clear all lists, cancel. I'm going to hit stat, edit. I'm going to enter these things in. I did it again. 55, 36, 25, 47, 60, 64, 42, 50. Notice these are the ones we had in before. They're the same ones. 120, 90, 60, 160, 190, 250, 110, and 150. All right, nice and easy. So now I'm going to press stat, calc, Lin Reg. All right, I got my regression coefficient. Now to enter y1 into store reg equation, position the cursor next to store reg equation, press vars. Select function from the vars manager, press 1 y1. So you can actually store these values. All right, so what I can do is I can go back to stat, edit, calc, and I can go to store reg. So if I go down to store reg equation, all right, say I want to store this part. All right, see down store reg equation, I could put y1 in there. I'm going to go next to here, and then I would just hit the variables button, which is right down here, vars. All right, and then what you do is you hit 1, which is, wait a second, press vars, select one function from the y vars. So you go over right to the y vars, select function, And then what I could do is I can actually put in y1 in there. Okay, so I can store that for later on if I want. All right, why would I store it later on? Well, say I want to use this equation again. All right, so what I did here was, let me zoom out. If you look on the bottom left, that's where I did that. So I went to this place right here, and I did the store reg equation. Okay, it gives me the same answer that I had before, but now it's stored for there. And that's putting the regression line in the scatter diagram. So now what I could do is, now that it's stored as y1, it's stored as a graph. So now I have it stored. I hit the buttons second y equals. See, this is stat plot right here. So I hit the light blue button second, and then I hit y equals. All right, I'm going to set up plot 1 as shown. All right, so the way it looks is, let's see, can you see my light on here? Not really. All right, so my plot 1 I'm going to turn on. So I enter next to plot, turn it on. I want to keep the dots, L1, L2, good. Mark in blue. You can make it whatever color you want. All right, now in order to graph that, so you want to graph it, you would just press the zoom button. The zoom button is right here. And this is how to graph this with the calculator. You're going to select 9, zoom stat. So I go down to number 9, hit zoom stat, and there's my graph. And look at that, it put a little line between it. This is an excellent way for you guys to check to see, make sure your stat plots are correct. Okay, so to make sure your plots are correct, very simple, you just have to do this part right here. You want to enter y1 into the store reg, and that's the way you can actually graph these things. If you don't enter y1 in there, it's not going to graph it on your calculator. All right? And our R1 was listed. We already turned diagnostic on. All right? Just going to try to give you as much info as I can. All right? Make sure I'm good. I am good. All right, number 2. Steve wanted to see whether there was any relationship between the temperature when he leaves for work in the morning and the time it takes him to go to work. He collected all this info over a 14-day period. So the first thing I want you guys to do is draw a scatter plot. So go. Now remember, you're going to throw the scatter plot, and eventually you're going to type all this information into your thing as well. I'm going to go type this into my calculator right away so I can check to make sure my scatter plot looks good. All right, so as you guys are doing your scatter plot, I am entering in my L1s and L2s. Might as well check your work, right? Eight, 34. I got my first column. There's 14 things here. 35, 42, 49, 31, 37, 33, 31, 47, 42, 36, 45, 33, 48, 39. All right. So once again, I typed all my stuff in. I just want to check my scatter plot. So just to check it, I got all my information in here. I go to stat, calc. All right. Vars. All right. Y vars. Function. Y1. Oh, I didn't put it in there. Did it too quick. Stat, calc. I'm going to do my linreg. Store. All right, that's when I go hit my vars. See, this is new to me too. Y vars function. Y1. All right, calculate. We don't care about this right now, but what we do care about is second, stat plot. My plot is on. So then I hit zoom. Whoops. Wait a second. Y equals graph. Zoom. That's a pretty crummy graph. All right, so that's my graph. Zoom stat number 9. So I'm looking at that, I'm like, wow, that's a weird looking graph, isn't it? Well, let's see if that matches up with what our thing looks like. Yeah, it does. And because I did that special graph, I can tell my linear regression line is probably going to be in the negative, probably going to be shooting down at something. Okay, so what our picture told us was it's going to look something like this. So I got our data, right? Calculate R. Okay, this is already done for us. So I have a calculator right there. Oh, look, I'm doing it over there too. All right, I have this video up there. I got all my stats in. I made these videos, but it's actually easy for me to just put it up there. Okay, so the way I calculate R again, I'll explain it as I'm typing it in. All right, I typed in all my things. I hit stat. I hit calc. I go to for lin reg. Enter, 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 enter. I turn this into a Y1, remember? And when I do that, I get my R, which is right there. Unfortunately, this isn't hooked up to HDMI, so you can't see it as great. Stat calc. I got this here. I got one right here. Stat calc. I didn't know I'd be so good with doing this. Lin reg. Calculate. There we go. My R is negative 0.21. Wow, is that a good R? No, that's terrible. We would not even use this line because we want at least 0.85 or negative 0.85 to use. This is an atrocious R. It's very weak. Negative 0.219. Remember 3 significant figures. So describe the relationship between the variables. Describe this. It's what? Negative. We said it was very weak, so it's a very weak negative correlation. All right? Between the two variables are temperature and time. That's terrible. Is there a reason? Is it reasonable to fit the linear model with this data? So is it reasonable to use this linear model to find other data? No, it's not. You know why? There's almost no correlation. Remember, you want about 0.85 or negative 0.85 to 1 or to negative. All right. There we go. That is problem 2. How are we doing so far? Good? These are the easy ones. Problem number 3. Problem number 3. Wait, how long is this lesson? Ooh. All right. Problem number 3. The table shows the process of petrol. Fancy word for gas. All right. And the number of customers per hour for 16 petrol stations. You have the petrol price, number of customers. Calculate Pearson's product movement correlation coefficient. Fancy word for R. So once again, you're going to go second mem. You're going to clear all lists. Remember, I'm doing this with you. You're going to stat edit, and you're going to enter in all the stuff. 105.9. Now, the big numbers go in the first column, not the second. 105.9. All right, make sure you're in the correct column. 106.9. 109.9. 104.9. 112.9. All right, and now after you do these, you go right to the next one. It's the same information. 107.5. Not a new graph, not nothing. They just ran out of space. 104.9. 102.9. 110.9, 106.9, 105.5, 109.5. All right, so you got 16. So I entered all those crazy numbers in. Now I'm going to do my second column. 5, 2, 5, 3, 15, 10. All right. Now right here I'm going to check, okay, 10, 112.9, good, they match up. It means I'm doing this right. If it doesn't match up, it means you messed up a column here. All right. Always check once in a while just to make sure your numbers are matching up. 7.5, good. That's when I'm entering stuff in. 30, 23, 42. Because you don't want to do all the work correctly, but just type in the stuff wrong. It's very annoying. All right. So I got all my stuff in there, nice and good. All right. You can scroll up. All right. I got all the stuff in there. It all matches up. Now I'm doing Pearson's product. I'm just going to do this with the regression line. Use that one again. So I go stat, calc, then reg, and I calculate it. I got negative 0.92598. That seems like a fantastic line. Don't worry about the r squared right now. My actual line is y equals negative 4.39, x plus 503, something like that. That doesn't really matter because that's not what it asked you yet. It did, but we didn't get that yet. So I put my negative 926. I don't know why I put 24 there. I should say 26. Describe the relationship. It's a strong relationship, negative correlation, and it's between petrol price and number of customers. All right. Find the regression line. Negative 4.27x plus 489. You know what that means? That means I entered in a number wrong. 5, 42, 25, 48, 43, 15, 19, 10, 30, 23. Now it's always good to check, because maybe I put my answer wrong. Huh. This bothers me when I get numbers wrong. 108, 107.5 is 30. And I'm looking up, I put 111 instead of 111.9. And that's what tanked my whole answer. All right? By just messing up one silly little number, it turned all my numbers wrong. Notice the linear regression line was very similar and very close to still the right answer. But this is what it should have said. It should have said negative 0.9237. That's why I rounded up to negative 0.9324. Notice it was only off by like 1,000th. So, and also notice that these two numbers were very similar. They're just a little different. And I use y equals negative 4.27x plus 489.43. All right, that's where I got those numbers from down there. All right, now we're going to use this info. What do we use this info for? Well, ready? We're going to take this info, and we're going to go to letter D. It says the table shows the process. Okay, so now we're going to state and interpret the gradient of the regression line. Now the regression line right here, negative 4.27x, so the gradient is negative 4.27. Now what does that mean? What that means is for every cent per liter of petrol, the price increases by, so every cent it goes up per liter, the number of customers goes down by approximately 4.27. And that makes sense. The more something costs, the less people are going to buy it. Estimate the number of customers per hour for a petrol station that sells petrol at 115.9 cents per liter. So we're going to use our, I just gave you an answer. So what I want you guys to do is, I want you to use the equation that we had. And in case you guys forgot what the equation that we had was, our equation is y equals negative 4.27x plus 489. So you use that information and estimate how much it costs when they sell petrol at 115.9 cents per liter. Got your answer? I think I gave you enough time. Well, the answer to that was about 5.10. Now, how did you find that? Well, this just equals, since it is 115.1 cents per liter, you just do negative 4.27 times 115.9 plus 489. And that equals about negative 5.10. All right? next one right now. Because that's negative 494.9 plus 49. So negative 494.9 plus 49, and that's how we get this number. Does that make sense? No, it doesn't. You would never have a negative amount of customers. Estimate the petrol at a petrol station which has 40 customers per hour. So now you're doing the customers. So in this case, you're doing 40 equals negative 4.27x plus 489. And you're solving it that way. All right? Got your answer? What did you guys get? All right, so answer you guys should have gotten here was, that's my clicker. Should have gotten about 105.3. So what you do here is you do this, and then you're going to subtract 49 from both sides, and unfortunately I just don't got enough space. You get negative 449 equals negative 4.27x, and then you divide both sides by negative 4.27, and you get about a 105.3 cents per liter. Now your last question says, which one's reasonable? And the answer of the ones that are reasonable. E, you can't have a negative number of customers, so that's just not good at all. So this is an extrapolation. It didn't fall within our values of our data. And F, though, that's an interpolation. And this does make sense. It does seems to fit our graph pretty good, so that is likely to be the reasonable. Right? And that's it. All right, how are we doing here? What did we get, about 2 days worth of work done so far? Yeah, about 2 days through. About 3 to go. Problem number 4, to investigate whether speed cameras have an impact on road safety. Data was collected from several cities. The number of speed cameras in operation was recorded for each city, as well as the number of accidents over a 7-day period. So, first thing you're going to do is you're going to draw a scatter diagram. All right, then you're going to calculate R. All right, then you're going to describe the relationship, find the equation of the regression line, state the gradient, and estimate the number of things. Now, I would type this in your calculator first, just to make sure you can check your line. So as you guys are graphing this, remember second mem, clear all lists is number 4. All right, and then you make your new list, stat edit. So let's get going. Five, 25, 16, 25, 15, 19. I'm just type. I have to always type it in right away. 48, 35, 31, 52, 53. Nice, it all matches up. All right, so we're going to draw the scatter diagram. That's what your scatter diagram should look like, with all the points. All right, notice it's going trending downwards. I have all my information in here, so I'm going to check my scatter diagram with this. And once the way I do that, I go to Stat, Calc. I'm going to go to my linear regression, which is going to have all my lines, But when I store, I hit vars, y-vars function, y1. I'm going to calculate. I'm going to come back here later. Oh, we could do our calculate r. Our r is negative 0.8698, so negative 0.870. Okay, so that's good. Let's see, is that my r? Yep, negative 8. Uh-oh, negative 878. I just can't type things into a calculator. 7, 15, 23, 16, 17, 28, 17, 25, 20, 5, 16, 25, 15, 19. Yeah, I have a problem with this calculator. Well, actually, my answer up there might be wrong. 52 is with 3. 20, 31, 15. Yeah, I think my answer there, my regression coefficient there is wrong. Uh-oh, I don't like giving bad data to people. All right, so looking at this data, easiest way to do this is with a plot. Zoom, stat. Let's check this out. Yeah, my data, my zoom data, looks very similar to that graph. Let's see, 1, 2, 3. A bunch of little guys by each other. Good, 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 good. I don't know. I think I have the wrong R there. Oh, when things go bad in class, but instead of just pretending like it's right, I'm going to check the book, and I believe the book is wrong. Now, you guys are probably either going to make fun of me because you got a different answer, or confirm that my answer was indeed correct. So this is 5 point something. This is 5D, and this is number 4B. 4B is my graph, negative 0.878. Yeah, I'm going to go say this is wrong. And I'm going to go right now say that when I hit stat, I'm going to clear my graph. A lot of times I just hit enter and just get off of it. Get off the blurriness, because no one likes blurriness. Stat, calc, linreg. I got negative 8.698, which is negative 0.870. All right, I'm going to go with that. I think that is correct. We'll see though, right? One of you guys may have the other answer. Maybe I typed in the button wrong. All right, so we're going to go to the next part. We're going to go to the losing my mind here. All right, so we're going to see describe the relationship negative 8.7. That is a negative, right? So it's strong because it's between negative 0.85 and negative 0.87 and 1. It is a negative correlation. Okay. Oops. Oh. All right. Next one, find the equation of the regression line. All right. That one you should have got negative 0.06. Plus 52.0. You know what I bet? I bet one of the numbers in the packet's off. What I got for this one, based on the packet, I gotta look at those numbers, is negative 1.04 plus 51.8. So if you got that, you're okay too. That's what I bet. I bet I put one of the numbers down wrong in the packet. But for what's on the board, that's my answer. For what's in the book, you gotta look at the answer. All right, state and interpret the gradient. So depending on which one you get, you guys understand what's going on now. The gradient, we'll just use the problem that's on the board, is negative 1.06. Okay? The y-intercept, so that means for every additional speed camera, the number of accidents per week decreased by an average of 1.6. All right? Y-intercept, this number right here, we'll say 52.0. All right, and the way that worked is, if there were no speed cameras in the city, an average of 52 car accidents would occur each week. Okay, and let's just use the equation they gave you. Estimate the number of car accidents with 10 speed cameras. So what you're going to do is you're going to type in that number. Ha! Found the problem. The problem was on the chart where those 224s were, in the 225s were. The book has 1724.25. The book, what I put in here, I made a mistake when I made this. I put 1725.25. So technically, the answer on the board matches the book. The answer in black matches what I had in the packet. I'm going to change the packet though, so go with what's on the board. All right, so estimate the number of car accidents in the city with 10 speed cameras. We take this equation, we're going to type in 10 for x. So negative 1.06 times 10 is negative 10.6. You're going to add that number to 52, and you get about 41.4 car accidents. All right? Not too terrible, right? All right, let's look at number 5. Gotta fix that now. Number 5 says the table contains information about the maximum speed and ceiling, the maximum altitude obtainable. So ceiling is the highest a plane could fly for a WW2 World War II fighter plane. The maximum speed given in kilometers per hour to the -1, and the ceiling is given in kilometers. So first thing I want you to do is take all this information here and use that information to draw a scatter diagram. I really hope that you guys picked the packets, or else this is going to be very annoying. Now I'm going to enter all my stuff in. Hopefully I didn't make another silly mistake, but this just shows you anyone can make mistakes. Even your wonderful teacher. Drawing your scatter plot. These things take a little bit of time to do, but I would also enter in the stuff. Whew. This one has 19 things you gotta enter in. There's no way I'm getting all these in right. Ooh, actually right on target. All right, so you should be almost done with the scatter plots. All right, so let's see how you did. Boom. All right, that should be kind of good. Is that what yours kind of looks like? If it is, excellent. If it's not, well, let's just see where you made a mistake. I entered in all those things. All right, so let's go check this out. I'm going to go now to Stat, Calc, LinReg. I'm going to calculate my R. Before that, I am going to store this so I can go check my scatter plot in a second. Calculate. And this tells me about my R that I got before I check my answer is 0.840 and the regression line is y equals 0.00812 x plus 6.09. I'm crossing my fingers, hoping that it's true. R 0.840. Whoa! Nice. I'm going to go to Zoom, 9, Zoom Stat, check my graph and my regression line. That is what I get. Notice, very, very similar to that. I'm trying to get them both zoomed in, but you can't. So that looks pretty impressive right there. All right. What do you think? Pretty good? Pretty good. All right, my regression line, number 4, as I said before, that's the one I just drew. And there it goes. The regression line was, oops, sorry. But yeah, I hit the button more down. The y-intercept is about 6.1, so it'd be really far over here, so we really can't draw that. But what I can do is, with drawing the regression line, is just using my technology to estimate. Okay, I know it goes to this point right here, and I would just draw it almost like a best fit. I know the slope also is about 6, okay, and it should hit, what is that? It should be about 611 is one of the intersections. If I type 600 in my calculator, I get 11, all right, and being that it's 6, so I can use like 60 or something like that. So I'm going up 10 over 60, up 1, over 120. Oh, my slope is 0.008. All right, table contains information, maximum speed, ceiling. All right, so describe the association. R equals 0.84, so it's not very strong, but it is a moderate, okay? So it's moderate, it is positive, and it is a linear correlation. And that's because it was 0.84. All right? Using technology, draw the regression line, draw a scattergram. We already did that. We said our regression line before. I already told you guys, 0.00812x plus 6.09. Went through some of the figures. State and interpret the gradient. Okay, the gradient is the thing next to the x, it's your slope. So the gradient is about 812 hundred thousandths. What does that mean? What's going on? What that means is, for each additional kilometer per hour, the ceiling increased by about 0.00812 kilometers. A kilometer is 1,000 kilometers is a meter. So if I multiply this by 1,000 or move this decimal place over 3 points, it means 8.12. That's a lot better than 0.00812 kilometers. So for every additional kilometer per hour, you can go up a higher 8.12 meters, which is about like 25 feet. Estimate the ceiling for a fighter plane with a maximum speed of 600 kilometers. So am I typing the 600 in for the y or for the x? It's my speed. What's my speed? My speed is, it says right here. Not even using my pointer that I just got. X. Alright? So 0.00812 times 600 plus 6 and 900 is about 11 kilometers. Alright? So the ceiling is approximately 11 kilometers. And that also is an interpolation, so that is a reasonable answer. Estimate the maximum speed with a speed of, for a height of 11 kilometers. Oh, look at it. Pretty much going backwards. So if you did 11 equals all that stuff, you would subtract 6.09 from both sides. You get 4.91 is of all that stuff. Divide it all, and you get about 605 kilometers per hour. Why are they different? Well, the only reason they're different is we did estimate. So when you estimate or you round, you kind of get a couple of kilometers an hour off, which is acceptable. And that's going to complete the nope. Not even close. I told you this one is a monster. This one's going to last a week. We got 2 more real problems, and then we got like a day or 2 of the other problems. Not fake problems, but just other problems. All right. Oh no. Sorry, I was zoomed out. Get back in there. There we go. Sorry, when I go from calculator to non-calculator sometimes, I just lose a little bit of stuff. All right. Problem number 6. A group of children was asked for the number of hours they spent exercising and watching television each week. Oh. Should exercise probably as much as you watch TV, but I don't know anyone that does that. All right, so let's draw a scatter diagram. What I want you guys all to do is draw your scatter diagrams. All right, we draw them. Scatter, scatter, scatter. So, scatter diagram should appear something like this. Does it? Does it? It does? Good. All right, now what you're going to do is you're going to type everything into your list. Stat edit. Let's get these lists going. 4, 1, 8, 7, 10, 3, 3, 2. Well, this is a quick one. 12, 24, 5, 9, 1, 18, 11, 16. Nice. All right, you get it all? Calculate R, second, stat. Whoops, why did I do that? Stat, calc. Linreg, I'm going to make sure I store vars, y vars, function, y1. Calculate. I'm going to go back to my scatter plot in a little bit. So first thing it says is calculate R. This is what I got when I typed everything into my calculator, so you know I am doing just as much work as you. Negative 0.927. What do you think? Good? I gotta go get my clicker. Click it on. And what do we got? We got negative 0.927. Good. Describe the correlation. Well, that's a negative, right? Is that strong, weak, or very strong? It is a strong correlation, all right? So, strong, negative, is it linear? Yeah, it's linear. Find the actual equation. All right, so I'm going to go back to my calculator. I have it right on here. Negative 2.13 and 22.1. Negative 2.13x plus 22.1. There we go. All right. And that is my regression line. That matches up with my other one. Problem number 6E. State and interpret the gradient and the y-intercept of the regression line. Okay? The way this works is also fairly simple. We had the regression line. The gradient was negative 2.13. And what that meant was for every additional hour a child exercises each week, they usually spend TV watching 2.13, all right? 2.3 hours. So the more they exercise, the less they watch TV. That makes sense, right? All right, the y-intercept, 22.3, all right, or 22.1. All right, and this is all based on the equation y equals negative 2.13x plus 22.1, the one we found out. All right, what that means is children who do not spend any time exercising would watch an average of 22.1 hours of TV per week. That is a lot of TV. Okay. One of the children exercise 7 hours each week. How much TV does this child watch? So we're going to use our line right here. All right. We're actually going to use the one from the group. One of the children in this group, so we don't even have to type it in here. What we're going to do is we're going to go, okay, in this group, which one watched 7 hours? You. you exercise 7 hours. Therefore, you watch 9 hours of TV a week. That's what was given to us. Right? Use the regression line to predict the amount of television. Now we're actually going to use this line. Okay, so y equals 2.13 times 7 plus 22.1. Y equals negative 14. Negative 15.01, right? Negative 15. I can't do that in my head. I tried. Negative 14.91. There we go. Plus 22.1. About 7.22 hours. So compare your answers. What does this mean? Why are they different? Why are they different? Well, the reason they're different is this particular child actually spent more time watching TV, right, than predicted. Is that allowed? Yeah, because we're just doing predictions. All right? That's it. We're doing the predictions. Problem number 7. The yield of pumpkins on a farm depend on the quality of fertilizer used. All right? Now, fertilizer versus yield. So first thing you're going to do is you're going to draw a scatter diagram to represent the diagram. Okay? And then you're going to identify the outlier. Remember, the outlier is the point that makes no sense. So now, I'm going to go back to my thing. You're going to draw your scatter diagram. I already did my scatter diagram. So I'm going to clear my lists. Oops. And get a little head start on. Let's go over here. A little head start on my chart entering stuff. All right, scatter diagram should be drawn. Looks like this. So when you're going to find out the outlier, pretty much the best thing to do is I go, okay, let me see. If I went like this, that'd probably be the best line. But that's not a really good line because almost all these points are above the line. But if I went like this, it's almost like a perfect line. There's just one little tricky point. That guy. He's my bad point. So therefore, my bad point would be my what? My outlier. So that little guy over there, he's my outlier. Now, what do you think that effect has on the strength of the correlation of data and the gradient of the regression line? So what do you think? Do you know? Well, let's check it out. 54.4 is the answer. So what? Let's see. So that's my outlier. So I'm going to find out both these things with and without the outlier. Number 1. What do you think though? Think is your thoughts. So it should reduce the strength, okay? Because this is out here, it messes up my gradient, okay? So what it does is it reduces the correlation coefficient because you have more of these guys now a vertical distance farther away from the regression line. And what do you think it does to this particular gradient? Okay? If I don't have it, my gradient's like this. If I use it, I'm going to have to switch my gradient like here. So what's going on with my gradient? It's actually decreasing the gradient. Now if my outlier was up here, it would increase the gradient. So depending on where the outlier is, that's how your gradient is affected. All right? So, now we're going to have some fun. And we end up with this. So we got a 0.798 regression. And our A is 0.0672 and our B is 2.22. So if we go to the calculate the coefficient with the outlier included, wait a second, 927, no, that's not right. So with the outlier included, the regression is 0. Well, they're both wrong. 0.798. Okay? Now the regression line, this one is correct. It's 0.06272 plus 2.22. All right? I just messed up that somehow. 7CI equals 0.798. All right? Now, without the outlier, sorry, you probably see the fuzz. No, you see regular. So without the outlier, what I'm going to do is I go back to my calculator, and I go, you know what? I got to take that outlier out. And the outlier that I'm taking out is right here. It's the 50 and the 0.44. So now, when I'm taking it out, I'm going to make sure I take this out of my list. So I don't want that in my list anymore. All right? So I go here in my calculator, and the way I take it out is very simple. Where are you at? Give me a little focus there. I am going to just simply hit Stat, Edit. I'm going back to my list, and the number that's bad is the 50, and the 44. So I go to 50, hit Delete, not clear, I hit Delete, go over to 4.4, and I hit Delete. Now they're both gone. And now what I'm going to do is I'm going to go back to Stat. I'm going to go back over to Calculator, and I'm going to go back to LinReg. Bam, 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 bam. Calculate. And notice, look what happens. Look how much better my regression is now. 0.992. That's almost perfect. All right, so my regression line now. And then my other thing is y equals 0.1187.119 x plus 1.32. All right, so this is 0.798. And then this one was so good, I just lost it. It was actually 0.993, which is very strong, and that's almost perfect. All right, so taking out that outlier made that problem so much better. Are we fuzzy? Of course we're fuzzy. We're always fuzzy. All right, so there we go. So we made it so much better by just taking out a little outlier. All right, taking out a little outlier. Never hurt nobody. Now, next one. If you wish to estimate the yield of 15 grams per meter of fertilizers used, which regression line from D should we use? Should we use with the outlier or without? Of course you should use the one without the outlier. Because, why? The reason for that is it'll be more accurate for an interpolation, okay? Look at 0.78 does not fall in the line. We want to at least 0.85 and higher. All right, 0.993, definitely good. Can you explain what may have caused that outlier? And do you think the outlier should be kept? Analyzing the data. So what do you think caused that? So the outlier was caused when we went all the way to the right. So when we used a bunch of fertilizer, it stopped yielding the pumpkins. So do you think? So we're going to say too much fertilizer often kills plants. That's what happened. Once you start hitting it up with a certain amount of fertilizer, you're going to start killing your pumpkins. So that's going to ruin our data. We only want the data in the area that is set up. So it should be kept. The data is valid. The data is a valid data value. It is true. However, if it was an error caused by bad measurement or recording skills, it should be removed. So what I would personally do is I would take it out and then just switch my interpolation from 4 to 35. Now say you had a value that was like above 35, like 40 or 45, then you would want to keep this data because then it would bring down your gradient, which would actually help your data. Okay? Got it? Got it, got it, got it? Good. Oh, now we're getting into the good stuff. So, that concludes the main portion of our lesson. Now what we're going to do is we're going to do something called residual plots. Now, this is like a bonus thing that's not really shown in your book, but if you go into your online book and you click on the button that says Residual Plots, it'll bring us to a bunch of extra problems. And I'm going to go over how to do all these problems for the next 2 days because I find these problems very useful. All right? So we're going to start with Activity 2. All right? What it says is, given a data set, we have seen how we could draw a scatter diagram, then find a regression line to model it. However, it is not always appropriate to model the data using a straight line. For example, the data alongside, right here, exhibits a strong positive correlation, but is clearly not linear. The value of R can be used to determine how well a linear model fits the data. However, to further assess the appropriateness of the linear model, we need to analyze something called residuals. Okay? Now, this line, as you know, where's my pointer at? Is more of a straight line, right? This is a straight line. It looks kind of strong. This one, though, however, is not straight. This line, if I wanted to do a straight line through this, would have too many things on the bottom and too many on top. So this is more of a curved line. So that would be more of a quadratic regression, which we're not doing until next chapter. Okay. Now the way to find this data is by actually finding out where the residuals are. And we could tell this. Now this right here is the one that was in the bottom right before. Now here's what a residual is. It states, for each data point, you are given by the following. Y obs minus Y pred. What do you think Y OBS stands for? That is the Y value that's observed of the data point. So that's the observed Y value of the data point. What do you think Y pred is? Well, so our Y observed is the actual points on the graph. So there's my Y observed. What about Y pred? That's the Y that is predicted. That's the Y value predicted by the regression line for the X value of the data point. So the predicted lines are the ones that fall actually on the line. So that's the one we're guessing at. Now they're not always the same. So here's how it works. You have a positive residual if the data point is above your line. So here's where I'm predicting right here. So since I'm predicting this, and this isn't going to the point, this is going to the line, I am this much positive residual. You have a negative residual if the data point is below the line. All right, so if this is my predicted, this is my predicted, my actual one's down here, I have a negative residual. That's how far it is from the x-axis. Now the residual plot plots the residuals against the x values. So it shows which points are above the line and which ones are below. So for instance, this one's a positive residual, so that one is above the x-axis. That's how much it's above. This one's a negative, so therefore it's below. See, 1, 2, 3, 4, 5, 6 points above. 1, 2, 3, 4, 5, 6 points above. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a big chunk of 10. That's this chunk right down here. All these points right here, these 4 above, those 4 above. This one almost on the line, this one almost on the line. So pretty much anything that's above the x-axis is above your regression line. Anything below your x-axis is stuff below the line. Now here's the reason why we use this, okay? The reason we use this is, if you have a pattern like this, see how this looks like a nice little loop going up and down? That's no good. That means your graph isn't linear. What you actually want is, you want points all over the place. You want the most scattered random amount of points you can have. That shows that your data is better. Okay? Now, here's how you construct a residual plot, and it's actually pretty easy. So what I did here was, I gave you some data, and this is my y values, this is my x values. Okay, these are my points right here that are observed. Okay, so the first thing is, we're going to use technology here to find out what the regression line is. So what I did was, and I saved you guys some time, just to get on with this, I actually went in and I, what am I doing? Alpha. Memory. I cleared all my lists. All right, I went into stat edit. I didn't clear all my list. All right, anyway, I did 3, 4, 6, 9, 11. Delete. All right, my second one was 7, 4, 10, 11, 20. All right, so for you, because I'm such a nice teacher, I typed all this stuff in already. I hit stat, calc, linreg, and I got this line right here. Y equals 1.61x minus 2.30. All right. So what I'm gonna do here is, we're gonna find the Y predicted for each data point by evaluating this for each X value. So what does that mean? Well, my observed values, so this right here is this line, okay? My observed values are, when X is 3, you got 7, 4, 10, 11, 20. So those are observed. Those are the ones that are given in my table, okay? Sure you're okay? You're positive you're okay? Okay. The predicted values, I'm going to take this 3, and I got 4.6. Where did I get that from? I did 1.61 times 3 minus 0.230. So what I'm going to do is I take all these values, okay, and go and multiply this by 3. I get 4.60. That's my first one. Now I'm going to go, okay, now I'm going to take this number and multiply it by 4. 6.21. Now I'm going to multiply it by 6. I'm multiplying by all these. Then I multiply it by 9, 11. And I just plug in all those numbers for X, and I solve it as you would solve a normal table of values. Okay, now, this gives me my predicted values. Now notice, what do you notice? They're not equal. So in order to find out what my residual is, this is my residual plot, and typically it's just a plot where you have the same amount of units above as you do below. Okay, it's always in the positive, you never have negative numbers. All right, or you could have negative numbers, sorry. I just don't know why I just lied like that. But you have positive and negatives. 7 minus 4.6, that's 2.4. So I would go 3 over 2.4 up. 4 minus this, it's negative, that's okay. Positive number, negative, okay. So you're just subtracting these to get these answers. Now when you plot these, 3 over 2.4 up, okay? 4 over 2.21 down, okay? Then you got 6 over 0.57, 9, negative 3.27, and then 11, 2.51. Now notice you're going like up, down, down, up, down. So you have kind of a scattered thing right there. If I wanted to see the best fit curve there, it'd probably something like almost like a horizontal line. So that is a good residual plot. And most residual plots are just all over the place. Got it? Now, we could do this with our nice handy dandy calculator. Now, I did put this information in before. And now I want you guys to type that information in your calculators and follow along with me as I do this with you. So we entered our X values in for L1 and our Y values in for L2. Stat edit, boom. Perform linear regression for the data set. Okay? So I entered in all my numbers. I already did that. You did that, right? Stat edit. We'll go back here. Oh, it was all fuzzy before. Let me make just sure you guys saw this clean. Sorry about the fuzziness. When I zoom in with the calculator, zoom out with the calculator, sometimes it just stays fuzzy. All right, so anyway, I do this. All right, now perform linear regression for the data set. What I'm going to do is find the residuals. They are stored in the list resid and can be accessed by pressing the second stat list and selecting resid from the names menu. What in the world does that mean? So that means I go into my calculator. I wish someone used to do this for me. I used to find this on my own. I press the second button, the light blue button, the stat button. Now I got some weird looking stuff. I got name, ops, math. I am going to the names menu. I go down to number 7. resid, otherwise known as residual. I press enter. Okay. Oh, shoot. Quit. All right, I did it in the wrong place. Stat, calc. Let me use my lin reg. Okay. What I'm going to do here is you want to store it in the list. Second stat. Resid. Calculate. All right. Now, if not listed, all right, we got our R listed, so that's good. So the number corresponding on the list resid may differ on how many lists you have on your calculator. Now, I don't know how many lists I have on my calculator right now. So let's go check this out. I'm going to hit second. All right, and then I'm at y equals stat plot. My plot is on. Go zoom. Number 9 is zoom stat. All right, and look what happens. So zoom, and then I go to 9, which is zoom stat. And look, there's my points, and then I got this weird line down here. So let's go check this out. Why is mine not right? Oh, I messed something up. The number corresponding to the list, stat, calc, lin reg. Here's the problem. You want to put your resid in your Y list. So your X list stays the same, right? So your Y list goes second list resid, which is number 7. So the X list stays L1, your Y list becomes resid. All right? And you can calculate this. Y equals, stat plot, X list is L1, Y list right here. This is the one I want to do. I want to do second list, resid. I like the color blue. Zoom, stat, and there is my graph. The line going across is just the coefficient line of the real graph, so you don't really need that on. I just don't feel like taking it off. Okay, so the key here is in Y, second Y under stat plot, you have to hit enter here. I forgot to hit enter. And then for the Y list, you turn this into a resid. All right, and then that will give you a residual plot. Got it? Now, what we're going to do is, I want you just guys to get a hang of this and match the scatter diagram to the correct residual plot. All right? Whew. Getting tired. All right, let me see what time. All right, so first one, this is how you do it. Look at these. 2 data plots above, 3 data plots below. So I look, well this says 2 below, 2 above, 2 on, 1 on. Now, look at this one. The answer has to be B, because there's 2 data points above and 3 below, and B is the only one that shows it, so that's your answer. Okay? So what do you think about letter little b? There are blank data points above this. How many? 3 data points above, and how many below? 2 below. So that would be C. 1, 2, 3 above, 2 below. Finally, little c, there are how many data points above the line? 2. How many data points below the line? 2. And 1 point where? On the line. And that would be, right? So that is how to match up data points to residuals. Right? Number 2. regression line is shown. This is our regression line in the diagram below. Which one of these residuals plots is for this regression line? So I want you to look at all of them and figure out which plot matches the line. All right, you should almost be done. We're making a good way through here. We're going to about to. All right. Not A. Why is it not A? Well, the reason is the values on the x-axis are not the same as these. Look at 0, 1, 2, 3, 4, 5, 5, 10, 15, 20. The values have to be the same. That's the easiest way to get rid of it. So now, let's go check. Okay, 1, 5, 1, 5, 1, 5. Okay, the rest are okay with that. So what about B? Does B look good? Not B either. Why not B? Well, look at, in this case, all the residuals are above, then all the residuals are below. But in this case, you have stuff above and below the whole entire time. So it has values that are more than 4 units from the regression line as well. And look at this one. This value right here is over 4 units away. None of these things are 4 units away. All right? This one, 5 units away. Look at this. There's nothing 5 units away over here. It'd be all the way down here. What about this one? That's an interesting one. Definitely not C. Why? Because all these values are where? Above the regression line. And here, you have some points that are below the regression line. All right? Let's look at D. Oh, winner. Yes, it is. The reason for that is all the values are within about 3. Right? This is a little bit more than 3, but pretty much within 3, above or below. Okay, and the values on this graph are all within 3 as well. And then as you can see, they're above and below the line all over. They're pretty scattered, pretty random. Right? And that's it. And this one's the farthest one away, and this one has the highest residual. Right? Number 3. The residual plot for discus throwers and the opening problem is shown. So this is the opening problem once again, but now I did a residual plot for it. Which of the athletes threw the discus further than the model predicted? Okay, so a bunch of those letters threw the discus further. So which ones do you think threw it further? Well, where do you think it is on the residual plot? It is the everyone that's above the x-axis. Those are above the line, so they threw it further than predicted. So that would be H, G, E, A, B, F, and I. Which athlete letter do you think performed closest to what the model predicted? So how do you figure that out, do you think? That is the one that is closest to the line. So what letter do you think is closest to this line? A? Oh, sorry. So this one was H, G, A, E, F, G, F, I. And this one said at the closest point to the line, either A or L. Which one do you think? It is indeed A. A is the closest to the line. This is about 1 finger width, more than 1 finger width. D's pretty close too. A is the closest. From that residual plot alone, is it possible to determine which athlete threw the discus the furthest? Can you figure out who actually threw the discus the furthest? No, you actually can't, because you just know how they are related to the actual prediction. But we don't know what the actual scatter plot looks like anymore. We just know what the residual looks like. All right, the residual plot only shows the distance, and the difference in the distance between the actual line and where they threw it. Okay. Very important aspect of statistics. And statistics is a class that most people take in college. This is very useful. All right, let's go to number 4. We'll fly into this stuff now. Number 4 says the equation of the regression line for the data points is y equals 0.92x plus 1.8. complete the table below. So what I want you guys now to do for number 4 is complete all the predicted values. So what you're going to do here is you're going to first start with x equals 3. Okay, so this is my regression line. So with x equals 3, what you're going to start with is plug in the stuff. So go. So let's go. You're going to take your 3, plug it into that equation. So it's 0.92 times 3 plus 1.8. This is 2.76 plus 1.8 is 4.56. So that is my I predicted. Now to find the actual residual, I do 6 minus 4.56 and I get 1.44. Do it for 4, 5, and 0.78. You're only using the x value to find the predictions. All right, so for 4, plug 4 in. As an answer, you get 5.48. So my y predicted value is 5.48. That would be where it would fall on this red line right here. And subtract the 2, you get negative 48 hundredths. Do it for 7. 0.92 times 7 plus 1.8 gives you 8.24. Observed minus predicted, negative 0.24. All right, now the way to graph this is, on the residual plot, I'm going to go 1 over 0.72 down. I'm going to go 3 over 1.44 up. I am going to go 4 over 0.48 down. I'm going to go 7 over 0.24 up. 0.24 down. So these are my points. Now, this doesn't show any clear pattern, so this is a very good residual plot. It means that my graph probably is going to be linear. All right? All right, let's go to number 5. Number 5 says, for this data set, what you're going to do again is you're going to find the regression line using your calculator. You're going to calculate the residuals and then use technology to check our answer. So, go. Type in your stuff. Type in your lists. So you go back to step, edit, 2, 5, 7, 10. This is an easy one to type in this table. 3, 9, 13, 16. All right, so the regression line you guys should have found. Those should have been those points that you plotted. Type in your regression line into your calculator. Oh, I already did this. Awesome. All right, so I have this. I'm going to just show you anyway. I'll do the rest of it later. Whoop, come on, zoom in, buddy. All right, so I got that. Stat, calc, lin reg. Uh-oh. What did I mess up on? I got a bunch of residuals in here. Calc, lin reg. Oh, see, I have the residual list in there, and I don't want that in there. I want L1, so I got to go back to variables, y variables function, and I got to go to L1. Oh, nope, L1's not there. Oh, L1 is number 1, so I can actually just go to stat. Anytime you need to get your L1 back in, under lin reg, see I have residual there. I want to put L1 back. L1 is light blue right down here, so I hit second, and then I hit 1. And then I'll put L1, but I want L2. So I have to hit second and 2. Boop. And now look at, I got my L1 and L2 again. Calculate. Oh, my arm is killing me. And I get this stuff, which, as you can see, I did on the board and copied there already. So I'm just going to use the board from now on. So my regression line is y is about 1.65, x plus 0.38. Calculate the residuals. So what I'm doing is, ready? Plug in 1 into here, and I get 3.66. You already did this on your own. I gave you plenty of time. Typed in 3 into here, and you subtract the 2, negative 0.66. All right? type the 3 into here, you get 0.40. Type in 4 into there, you get 11.50, which is 1.10. When you subtract these two, why are my numbers all so far off? And then 16.84, 0.84. Wow, something really messed up here, I think. 3 times 1.65 plus 0.368 gives me, these numbers are all messed up. It should be 5.318, and then when I subtract 6, it is negative 0.682. Is my regression line wrong? Hold on 1 second. (1.65) x plus. All right. So let me just do this real quick just to make sure I didn't mess up. 1.65 times 2, times 1, right, plus 0.368. That gives me, oh, my numbers are off. Oh, my x's here are supposed to be 2, 5, 7, 10. All right, and these are supposed to be 3, 9, 13, there we go, and 16. All right, I have my x's and my y observed wrong, but then after I do that, everything comes up. All right, sorry for that. This is number 5. A. Okay, x and y. See, everyone makes mistakes, except for, but this work was right. I just, when I copy paste this, I copied it wrong. So anyway, 2 over negative 0.66 down, 5 over 0.4 down, 7 over 1.1 down, and 10 over negative 0.84 down. And that right there is my residual plot. All right. Whoa. All right, let's go next one. This is why it's good doing this in school. I can't, because when I do this at home, I can't draw on my TV. I got all good now. Okay, we're back. Okay, so 5B. Draw the regression line. All right, draw the scatter diagram. So I can actually go through these quickly because I don't have to do the work anymore. I can just pause and play. So the scatter diagram you should have drawn should look something similar to this. All right. When you find the regression line, you type in your calculator. You get A is 0.743, B is 5.47. Okay. So our equation is approximately, y is approximately 7.43x plus 5.47. The R is 0.984, which is really, really, really very strong, which is good. Okay, looks pretty strong to me there. All right, now we're going to find our predicted values. We'll plug 3 in here. 0.743 times 3 plus 5.47 is about 7.69. Subtract the 2, you get 0.31. And typically you don't really want your residuals that large either. Type 7 in here, 10.66, residual negative 0.66. Type 8 in for x, you get 11.41, 0.59. Type 11 in, you get 13.63, residual is negative 0.63. And you type that one in, 16.60, residual about 0.4. You plot the points, you notice they're all over the place. They're very similar to the distances they are away from the x-axis, which is good. It means they're pretty much all the same distance away from your residual line. All right. It's 5B. Now we did 5B. We'll move on to 5C. All right, 5C says for each data set, What you're doing here is you're going to type all those into your calculator now. Now we're doing a group of 6. All right. First one, you plot your points. Looks pretty okay. The red and the blue are kind of a little bit out there, but for the most part, it's not too terrible. You want to type your stuff into your calculator of your lim reg. You get negative 0.94, 7x plus 17.8. Okay? I got the same thing. That's actually a picture of my calculator. And then you can plot that line if you'd like. Y observed, Y predicted. What you're going to do is you're going to type in your x's, 1, 9, 6, 15, 4, and 12, all in for x. And you get 16.8. Your subtracting difference is 1.2. 9.23. You subtract the 2, you get 4.77. These are all your residuals. 12.07. Subtract 2, you get 0.07. That's a really good one. That means it's almost right on the line. The blue one, 3.55. That's about 1.55 away, negative, so it's a little bit lower. 12.96. Negative 3.96. 6.39, and that gives you 0.39. Plot the points, and there's the points. All right, any questions? No questions? The only difference is this point, I just messed up the red and the blue colors. I just mixed the colors up. All the data is correct, but the colors for these are messed up. All right, because obviously if I did my graph, my line right here, this one is another colors, right? These colors wrong. This one should be blue, and that one should be red. As you can see, this one's the farthest above. This one's the farthest below. This one's right on. This one and these are really close. All right? That's how you can tell. All right. Residuals. What do we do after residuals? Going here. The equation of the regression line is applied to the data alongside. Okay? Diagnostic blood pressure. So now this is used in the medical industry. 68.5 plus 0.2 times your weight. That's what your blood pressure should be. All right, what we're going to do is we're going to draw a regression line of the data. So in order to draw the line, we're going to use this equation. Okay, now how I did this equation was, I said, you know what, I can't go to the intercept over here because it's cut off. It kind of cut me off. The intercept's about 65.8. So technically, I guess I could put a point here at 68.5. And then the 0.2 means I go 0.2 up, 0.2 over. So what I did a little bit different. I took 2 points. I said, okay, at 60, and this is how I graph this. I type 60 in here, all right? That is 12 plus 68.5 is 80.5. So I said, you know what? 60, 80.5, I could put a point. And I put a point on my graph. Then I said, you know what? I need a second point. Let me get something similar to 60. I'm going to go 90. I'm going to go over a little bit. So now if I go 90, I can find out where my point of my residual line falls on this 90. That's 18. 18 plus 68.5 is 86.5. So I have a point there. 90 over 86.5 is up about here. I connect these 2 points, and that gives me my actual residual line. Okay? Now, 68.5, the reason I don't put it here is, this would only be about 50, because this little break here means I still have 50 to go. So it does hit 68.5, but it hits it somewhere here off screen. That's why you have to pick your 2 points. All right, so we draw a regression line, estimate the residuals for the following points. So we're just going to find 2 residuals. The first point is 82, 87.5. So what you do is, you're going to take your x value, and you're going to plug it into this equation and find out where you think it could be. Go. All right. So 82, 87.5 is this point right here. The residual will be right where it crosses the line here. And where does it hit this line? At 85. So it's about 2.5. That's how I find it from the graph. Now if I wanted to find it mathematically, I could just type in 82 into this equation, and the way I can use that is 84.9, which is about 87.5 minus 84.9 is about 2.6. All right, so that was using the graph, and that was checking it with the equation. So why don't you guys try problem 2? All right, problem 2. What do we do? That's this point right here. 103.3. 81.4, right? So let's take this guy, put him up to the graph, move the graph over so it hits about here. This is about what, 85, 86, 87, about 89-ish. All right, so about 89 from the graph. So to find the residual, 81.4 minus the 89, which is our estimation, right? The difference between the two purples, and that's about negative 7.6, right? What do we do next? Plug it into the equation. When you do that, you get 89.16. You're pretty close to their estimation. Subtract that from 81.4 and you get about negative 7.76. All right, so our answer is very similar, very close, if not almost precise. And then finally, problem C, sketch the residual. Okay, now the way to sketch the residual, use technology. Don't kill yourself. All right, so I can't really type this in using technology. The best way to do this is your graph would look something like that. Now the way I would sketch this is I would just do this. Okay, this is about two-way negative, so I put this here. Right, I go about 3, maybe 4, a little bit more, a little farther away. This one's under. Okay, so just based over there, like an under and under. All right, and over. 3 unders, 1, 2, 3. All right, then you got an under and under, under, close under, and then you got a bunch of overs. All right, so that's just a sketch. We're really supposed to go into it because we don't have the actual data. Unless you want to take down all these numbers from the data and then go them against here, but then that would just take forever to do. All right, and I just want you guys to get an idea of this stuff. And that's the class. No, that's not the class. That's the first class. Now we're going to have a quick discussion. All right, now this discussion right here. Just trying to see how much. 44. All right, so why is the sum of the residuals always 0? Why do you think when you add all the residuals together, it's always 0? You have an idea? Because they're supposed to be the same distance away from the top and the bottom. If you're only given a residual plot of a regression line, will you be able to determine whether the data is positively or negatively correlated? What do you think? Will you be able to tell the strength of the correlation? Whether the data is linear or linear? I can tell you right now, you can tell 2 of those. Think. And then we're actually going to discuss this as a class as opposed to discussing it now. All right. Part 2, analyzing a residual plot. All right, so we did the residuals, we did the plots. We got about 1, 2, 3, about 4 pages left to go. So this is almost like a whole lesson in itself. Now, we can use residual plots to determine whether it is appropriate to fit a linear model to data. So you have two cases here. Case A states the set of data points appears to be linear. Its regression is also shown. Okay? So, here's the residual plot for this data points. The points are randomly scattered all over about the x-axis, which I mentioned before, with no obvious pattern. Since the data varies randomly about the regression line, we can conclude that the linear model is indeed appropriate for the data. So because these points are all scattered and there's no definite, like you don't see like a U or an upside down U or like a wave with the residual, that means that this is most likely a linear graph. They're just the same distance away. Case B. The set of points do not appear to be linear. Okay? On the residual plot for this data, the points, we see the points are not random. But you could actually almost connect the dots and have like a pattern here. Okay? But they show a clear pattern. We can conclude that the linear model is not appropriate. So it's not going to be a linear model. So look at this one. This is almost like an exponential or a quadratic, one of those two models, right? It's raised to a power, obviously. So if we cut this with a line, all right, we can notice it's above, 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 below, 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 above, above. And the distance goes farther and closer with the pattern. Because of that, we realize that it is indeed a quadratic. Right? So residuals actually tell us what type of line we're dealing with and tells us which type of regression line we should use from our technology. See, told you this gets so tricky. In general, see, a lot of this stuff we don't have to do work, we just explained to you. A residual plot with many points randomly scattered all over the x-axis indicates that the linear model is indeed appropriate for the data. A residual plot that shows a clear pattern, it's not appropriate for the data. Large residual values may also indicate that the linear model is not appropriate. Okay? Move on. First set of data given is an ordered pair. You have a bunch of points there. And we went over Pearson's product correlation, I think a lesson or two ago. You had the means of the x's, you had the mean of the y. You take the sum of the differences between the mean value and the actual point value, right? When you multiply the two, and then you take the square root of the sums of the mean value subtracted from the actual point squared times the mean value of the y value from the actual point squared. All right? You're not required to relearn this, but this is what your calculators do. Be appreciative of your calculator. For example, consider the following data set. Use technology now. You better be experts at this. Not you should, you better be. Find the coefficient and the regression line. So regression line and the R. Okay? So type in second mem. They're all lists. I was going to do 2 lessons today. This one's taking forever. I think this will take about a week. So that's good. I'm going to type in stat, edit. We go to 1, 2, 3, 4, 5, 6, 7. Okay? We do 0.75, enter. 1.95, enter. 3.1, enter. 4.2, enter. 5.1, enter. 5.95, enter. 6.7, enter. All right, got all my stuff in. So you get all your stuff in. Whew, get in there. Give me a little zoom there. There we go. And you know the buttons, stat, calc, linreg, experts, right? Enter, enter, enter. You know what? I'm gonna put a little picture in there. I'm gonna throw a little bit, show I know some stuff. I'm gonna throw a little function in there. I'm gonna put y1 in to store it, and I'm gonna calculate my answer. So as you can see, 0.996, that's a really good one. And we got our numbers right there that we're gonna use to find the y's. Whoop. All right, and we got a regression, which is a very strong positive. Use the technology, we obtain the residual plot shown. Well, that's not the residual plot, but I can find the residual plot right there. Now, how do I do that? Well, let's check this out, because it looks like everything's on the line, but how did I get the residual plot? Well, I took this information I got right here, I'm going to tell you again because this is a very helpful tool. Save a lot of time. I go to y equals, second stat plot. Plot on. My y list is my residual, remember, okay? Leave that as my residual. And in case you forgot how to get to the residuals, it is, stat. Nope, not stat. Edit. Where was it? I just forgot what it was. List. Names, and you go down to resid, number 7. Okay. And then I'm going to go to zoom. 9 is zoom stat. This gives me my graph all nice and zoomed in. And that's how you got the graph. Okay, so just remember, you have to get the residual. You have to put it in your stat plot. So that's a pretty good graph, but wait a second. Looking at that graph, does that graph look linear? It looks linear on the line. It looks linear on the problem. But when I look at my residual, does that look like a linear graph to you? No. So even though, watch this, even though the R is almost perfect, it's so nice, does not necessarily mean that the linear model is appropriate. The original scatter diagram, the correlation coefficient, and the residual plot should all be considered before using a linear model. So I would look at this and be like, oh, that's great, definite linear model. But when you get to it, I look at this and I'm like, uh-oh, that's not good. This means that this graph is actually a quadratic. Even though it's bending really slowly, it is bending, okay? So it's not a linear graph, even though all the other information tells us it is. So when you get to like high level statistics, residual plots are very, very important. All right, that's why I wanted to stress this whole lesson to you and get into this stuff. You got it? All right, what do we got? 3 more pages from the book. 1 more set of problems. And I'm missing my clicker. All right. So what I want you guys to do is problem number 1 as I'm finding my clicker. What am I at? I'm almost at 2 hours here. This is, need some wind. Which of the following residual plots shows a regression line that is good for the data? Oh, this is just like the one we did before. Which one of those residual plots is a good one to have? You got your answer? All right, the answer is the residual plots for A, B, and D show points that are randomly scattered with no obvious pattern. Is that good or bad? Boom, that's good. So those are the good ones. The one in C, look at the pattern. Above, 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 all below, above, above. So it's almost like a U. So that's a non-random pattern. There is no pattern. There is a pattern there. So the residual plot for C shows a regression line that is not a good fit for the data. The ones that are a good fit are A, B, and D. Okay? You got it? All right. Number 2. The set of bivariant data and its regression line is shown. All right. Which one is the correct residual plot for the data? So here's your actual data. Which one of these residual plots matches it? All right. And the answer is not A. Not A. Because most residuals are above the x-axis. Almost all these are above. This scatter diagram, the scatter diagram, been going a while here, only has 3. See, there's only 1, 2, 3 data's above. So if I want to do this, I could say above 1, above 2, above 3. So there's 3 above. All right. There's like on 1, 2, 3, I don't know, almost 4, 5, 6 are almost on. And there's really only 1 below. All right, so most of these things are really close.
Please report to the main office. Report to the main office.
What about B? That's not good. Because most residuals are above the x-axis. This thing only has 3. Look at this, 1, 2, 3, 4, 5. Now look at this. Even though these aren't on, they're all very close. So C and D, are they the same exact graph? I think they're the same graph. I messed this up by copy pasting. C is yes, because most residuals are below the x-axis, and these ones are slightly below. They are on, but they're just a little bit below, which you see right here. One big one below, the 2 big ones above. All right. This one's a no because most residuals are above the x-axis and the data below it. Oh, so I messed that up. 2. Just ignore 2. These points should be, I think, like this. All right, 2D, 6 points on. All right, see, told you. Everyone makes mistakes sometimes. Did I mess it up in the packet though? Yeah, I messed it up in the packet. My bad. Number 3. I hate when I have the right answers, but I mess up the actual work. But like I said, this is the first year I made it, so there'll be a couple mistakes. Tigers basketball team has 8 players. Oh, Legend Tigers. After a match, the team statistician performed a linear regression on the scatter plots of the points scored versus the shots taken and scored versus uniform number for the players on the team. Below are 2 residual plots. All right. Do the points in the residual plots appear to be randomly scattered? What do you think? Yeah, it's pretty random. For which data set is a linear model more appropriate? So what do you think is more appropriate? Shots taken, or versus points scored, or uniform number versus points scored? Which one's more important than linear? Points scored versus shots taken. You know why that is? The residuals here are smaller, okay? Notice this one's only 3 to -3. This one goes from 10 to -10. And you want smaller residuals, they're better. Meaning the points are generally closer to the line. All right? Another thing just to be said, your uniform number really typically doesn't make a difference of how many points you score. All right? Because you can pick whatever number you want. That's why these, even though they're scattered and they're crazy like that, that's why the numbers are more off. Right? Problem number 4. For each data set, draw a scatter diagram. Use technology to find the regression line and state the value of R. Construct a residual plot. Determine whether the regression line is good. So we're going to do 3 of these. And then we do 5. And 6. And then we're done. We're not really going to do the discussion. Whew. This thing ate up all my data in my phone too. So I had to go erase all my stuff. Alright. So I'm going to take my graph. You're typing this all into your calculator. Make sure that you constantly are clearing that calculator. Alright, so second mem, number 4, clear lists. Alright, so you're entering in stat edit. You go into here. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, 33, 29, 25, 24, 20, 18, 13, 9, 8. All right, so you got your stuff there. So did you draw your scatter stuff for your scatter diagram? Stuff for your scatter diagram. All right, if you want to check your answer, you can go stat plot. X list, Y list, pretty much the same. X list L1, Y list, I'm going to make L2, zoom 9. So I can actually put this on my calculator. All right, look at on my calculator. Looks pretty much the same. Actually is the same. All right, now it also says, use technology to find the regression line and state the value. So you go into Stat Calc, LinReg. All right, you really can't see that in the bottom corner, I bet. Nope, you can, no, you can kind of a little bit. Let me zoom in on my calculator since I spent all this time typing it in. That's really what I got. All right, I'm going to use that information. Whoop. Negative 3.166 or negative 3.17x plus 35.7. My regression value is negative 0.994, which is a very, very, very strong. Now we're going to see if this is actually a decent graph or just a trickster graph, if we really know. What we're going to do that is we're going to use technology to construct the residual plot. So instead of just going in and doing the big long table for residual plot, we're going to use technology. Now I told you how to use technology before for the shortcut. What you do once again, you go into your calculator and hit second y equals, and I'm going to make this plot 1 again. I'm just going to change my plot. Go down, down, down. Instead of L2, you're going to hit Instead of L2, you hit second list. Second list is where the stat is. Go down to number 7, which is resid. You're putting it in for your Y list. Then you hit zoom, hit the number 9, zoom stat, and then it gives you a plot that looks like that. Okay, how can I match this up? I could say, okay, I could just put these points on the plot, and my points on my plot look like that. This is a little furry, but as you can see, same exact thing. Determine whether the regression line is appropriate. So, are those points random? There's a very strong correlation, so that's really good. Are those points random? Residuals are random. The least square regression line is indeed appropriate for our data. Okay? That's it. That's not it. Here we go to the next one. All right, so for the next one, B. More things to type in. All right, stat. Edit. I'm going to type them in with you, just to make sure you guys don't cry. It says you did all the work. 2.2, 3.7, 9.5. Not that there's anything wrong with crying. 9.5, 6.2, 1.4, 3.9, 7.5, 8, 5.5. Whoo! 3.6, 7.1, 22.5, 22.5, 13.3, 1.9, 7.6, 16.8, 18.2, 11.5. All right. Scatter diagram, you can do on your own. Looks like that. Technology shows it's about the same. Looks like a pretty strong one, right? That looks pretty good to me. I don't know about you guys. So technology to find the regression line. I typed in all my fun stuff right here. All right. When I typed it in, I am going to hit the buttons that say stat, calc, linreg, calculate. And I get this. Oh boy, that's a lot of stuff. All right, so I get all that. Looks pretty impressive. And then that is the same thing I got on the board. And I got 2.54x minus 2.11. My regression coefficient is 0.999. Can't get much stronger than 0.999. That is nearly perfect. So I would say, yes, this is definitely, oh wait, now I gotta do my stupid residual though. Residual might ruin it for everyone. So once again, I go back to my calculator. I'm gonna go like, you know what? I'm just gonna use my calculator's residual. All right. And like I said, you're just estimating this stuff on the board. So my residual right here, I go back to second stat plot. Oh, it's already listed as residual. Zoom, 9 for zoom stat. And uh-oh, what is that showing me? Is that random? Those points? So the residual the residual plot shows a clear pattern. They do not appear to be random. So even though this almost looks like a perfect line, the least square regression line is not appropriate. Nearly perfect. But it's just the slightest quadratic. All right, so you'd have to use a different line. That's why residuals are important. Who wouldn't think that's a line? I think it's a line. I thought it was a line until 2 seconds ago when I saw this plot pop up. You have to be careful, have to do your residuals. All right? Just make sure they're clear. 4-point C. All right, type some more stuff in. Let's go. Let's finish this lesson strong. Edit. All right. 5, 9, 1, 12, 6, 5, 9, 7, 2, 10. All right. Scatter plot, scatter plot. Ready? Scatter plot. Boom. And you can use your graphs. We're going to be using our graphs to find our scatter diagrams. That looks pretty junky. That doesn't look like a great scatter plot, does it? Well, I'm going to go to Stat, Calc. I entered in all my stuff. Enter, 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 enter. And what I got for my graph is, 0.385 for an R. Ew, that's ugly. Right there, that tells me my graph is, my points are garbage. Let's see if I matched up or I messed up somewhere. 0.491x plus 4.56 and 0.385. Yep. That is a terrible regression, but we can check out our residuals anyway. All right. So to check out our residuals, what we're going to do next is very simple. All right. So we're going to keep on going. To check out our residuals, we go to here, back to here, and we're going to go right back. Our stat plot should already be good. I'm going to go back to stat plot again, though, second stat plot, just to check. All right, guys, see that residual? Go to zoom, down to number 9, zoom stat, and then, oh, that's pretty impressive. Go check it out. Check out my red residuals over there. Got the same thing. Looks like the same thing to me. Yep, got the same thing. So I estimated. It's random. So the value of R is very small. Very weak correlation. Least square line is not appropriate. So even though our residual plot's good, this is the type you want, our R is so junky that we can't use the line. So you can only use this line to predict data if your R is good, above 0.85 to 1, or from negative 0.85 to negative 1, and our residual plot's random. So you need both things true. One of these things is bad, line's terrible. Don't use it. You got it? And that is the gist of everything. All right, let's go finish it up strong with number 5 and 6. 5 and 6. I have every piece of equipment I have right now is about to die, so we have to go quickly. And I have it all charging and all this stuff going on. All right. All right, so first off, draw the scatter diagram. Oh, I can tell right away what that is, but that's scattered. So I plot my points, points are plotted. All right. All right, let me go second, mem, clear. I'm starting to get my second wind right here. Stat edit, so as you can see, I'm doing this right here with you guys. 6, so that's your scatter plot. Your scatter plot should be good. 4, 5, 8, 7.5, 10, 7. Look how quick I put these in. And I always check with technology my scatter plot. All right. Whew, so we use our technology again. So I got all my stuff right here. Typed it all in, and you know what to do. Stat, edit, oops, sorry, stat, calc, and then reg, calculate. Ooh, R, negative 0.952. I like that. So it's y equals negative 1.49 plus 19.6. Let's check it out. Typed in our thing. Negative 1.59x plus 19.6 with a regression line of negative 9.53. A very strong negative correlation. Draw the regression line on your scatter diagram. So now we need to see the regression. So once again, we go to zoom. 9. Oh no. What is that? It's what I told you it would be. So when we do this, guess what our regression line looks like? Looks like a U. Looks like a parabola. Exactly what we predicted. Because you can kind of see the U here. The U here. All right? The more you do this, the more you can see it. Use technology to, oh sorry, this is our regression line right here. We did this one. Technology construct the residual plot. We did that. Is the regression line appropriate? Right, residual line shows a clear pattern. Okay, so this is really just the best eye fit line. So this, good, pattern bad. So the residual does not appear to be random, and the least square regression line is not appropriate for the data involved. All right, and that's number 5. Feeling it? All right. You guys got to split this up over a week or so. I had this all one. Yeah. Number 6, the last question of the day. 10 people are asked how many text messages they had sent and received in the last week. Oh, we're going to go back to the text messages. All right. Draw a scatter diagram. So let's go. Let's finish it strong. And let's do the scatter diagram on our calculators as well. So we're going to start with an edit. Let's do this together. 18, 3, 7, 22, 15, 5, 20, 30, 7, 25. You doing it with me? Come on, teamwork. All right, let's do the second column. 22, 2, 9, 21, 16, 9, 23, 33, 7, 24. All right, scatter diagram should look something like that. Now, how do we find a scatter diagram in our calculator? Once again, right now your calculator is set up for residual plots. So you just go to second, stat plot. Here, we're going to turn that, get that resid off, okay? Or a way to make this easier is you could just turn this plot off. Okay, go up and go to plot 2. We'll just use a different plot. All right, and we'll plot that one. We'll turn that one on. So now when we plot this one, same thing, but then we can always go back to the resid. We type zoom, we type 9, and then that is the points we have, and you can see a regression line going through those points. Okay? So we have our regression line, we have our points, and that looks pretty good. I'll be honest. I think we're gonna be good with this one. I hope. Find the regression line. So we're doing this together, remember? So we're gonna go to stat over 1 calc. we're going to go down to linreg. We're going to hit enter a bunch of times and hit calculate. Okay? Now, when we hit calculate, so it's y equals 1.01x plus 1.24. And our R is 0.9767 or 977. Hopefully, let's go check it out. Boom! That's the one I did the other day. There we go. 1.01x plus 1.24 with the value of R of 0.977. A very strong positive correlation, which looked like that when we did our graph. Construct the residual plot. Calculator time. All right, so, ready? Here's the trick. Going back on our calculator. Oops, sorry. That's all there. And we're going to go back to our calculator right here. And what we're going to type is, we're going to go back to stat plot. We don't want plot 2 on anymore, so we're going to turn that guy off. Go up to plot 1. Hey, get out of there. Stat plot. Stat plot. Go back to plot 1. Turn that bad boy on. Zoom. Zoom stat. I don't know what that graph I put on there is. But that's what my residual should look like. And according to me, I put those guys right there for you. What do you think? Good residuals, bad? I think it looks pretty good. Notice anything about the residuals? They're random, right? Which is good. Describe the correlation between the text message received and this. Well, very strong and positive. Right? Now the last thing to do is figure out, is it linear? So let's look at E. Is the regression line appropriate for the model? Of course it is. There's a very strong positive correlation. The points are random. Therefore, the regression line is indeed appropriate for the data. Right? Ted here received 10 text messages last week. Estimate the number of text messages he sent. Now, just so you guys know, the equation we said before was y equals 1.01x plus 1.24. Okay? So since y equals 10, can we find out how many he sent? We know he received, this is where we get the y from, received 10. So that's where y equals 10 comes from. You just do 10 equals 1.01x plus 1.24. Subtract 1.24 from both sides. Divide both sides by 1 and 100, and you get about 8.67. Let's see, do you think this estimate is reliable? So 10 for our y, yep, look at this. As long as the number is between 7 and 33, it's an interpolation. All right, so about 9. Fairly reliable. It's between our two values, 7 and 33, the 10. So it's an interpolation. It was a strong graph. Regression had been doing pretty good, so it is a fairly reliable. And this is the purpose. This is why you're doing all this stuff, to create the word problem stuff we're going to do next. All right? But now you're just checking out, can I actually use my data? Right? All right. Whew. Interpolation, like I said, with strongly correlated data. And that's all you can ask for. All right, so a little discussion that we may have. When we generate our least square regression line, our aim was to minimize the vertical distances between the data points of the line. Okay, that's the distance from the point to the line. Vertical, 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 vertical. Okay, that means when we use the regression line to estimate the value of y, given the value of x, we can make sure the error is minimized. So we want these numbers summed to be as small as possible. We pretty much want it to be 0. The second graph shows the same data. But now, what if we went a horizontal distance from the line? All right? Do you think that will work? Coming up with an equation that did that. What do you think? We're going to discuss this in class. We're discussing it right now, of course. All right. So, the two questions I want you guys to discuss with each other, then we'll discuss as a class, is do you think the regression line also minimizes the horizontal distances between the data points and the line. How would it be different if we tried to minimize the horizontal distances instead? We're going to suppose we use the regression line to estimate x given the value of y instead. Can we be sure that the error in this estimate has been minimized? Will this estimate be as reliable as estimate of y given the value of x? Okay, so this is some things we're just going to discuss in class, but not on a computer screen. I think over a 2-hour lesson is plenty of lesson for you guys. Hopefully you learned today and this week, or now maybe 2 weeks, about the least square regression line. You can interpret the least square regression line, draw a scatter diagram, use the regression coefficient, calculate the regression plot, and that the most important thing is you know what all these things mean and how they're applied in real life. Okay? So until the next time I see you, have a good day.